Hello class, welcome to today's lecture. I'm looking forward to interact with everybody today. So let's first do a recap about what we talked about in last lecture. In the previous class, we have been focusing on discussing what is different coil size in polymer, and this coil size is quantified by contour length, the end-to-end distance, etc. So today's lecture, we're going to continue to do that and start discussing a little more detail on these different chain models. And in the past lecture, especially the last one, we have talked about two important parameters. We discussed the concept of random walk, how random walk would be related to how you can change the chain's statistic to understand where your last step or the chain end will be ended up. This is very simple and can help you to visualize the chain conformation in three-dimensional space. Additionally, we have discussed about the role of free joint chain and how free joint chain, despite it is a very simple model, it can help us to understand how the Gaussian coil would look like, or a typical polymer coil. In today's lecture, we're going to start to consider a little bit more realistic example. So in the ideal polymer chain or free joint chain, the bond can rotate at any angle, and only limitation is the bond length is fixed in that case. But as you know that in real case, as I spoke many times, the sp3 carbon has a fixed bond angle. And such bond angle would impact your polymer coil size. So to start off, I want everybody to think about what actually those coil size could be and how you think that the bond angle would impact your coil size compared to a free joint chain. Will it increase the coil size or decrease? If it changes coil size, how big the degree of expansion or compression will be? So today's lecture, we will dig deeper into those two concepts and discuss with everyone how we can use some very simple treatment to get what we call it a free rotation chain model. And if we get some more time, we will get into more complicated rotation isomer model. So let's get started today. We already discussed all the random walk and how does the end-to-end distance for ideal chain will be ended up with NL squared as shown in this particular slide. So if you still have questions, let me know. And you should not have any because this is the most fundamental one. In next slides, we're going to discuss about the end-to-end distance with respect to different chains. And end-to-end distance is basically defined as a vector r as shown in here. And end-to-end distance is a preferred method to quantify how big your polymer coil size. So one concept we want to discuss is that concept of projection. So if you have a bond going into one direction as shown in this Li bond, the next bond will be Li plus 1, will be the bond sitting next to it. And if you know the bond angle, you can calculate about how much degree of persistence, meaning it. So this bond will follow in the same direction as the previous one, how much degree of following it has. So if you compare these two, as you can tell, how much the bond Li plus 1 has been following the previous chain will be equals to this bond length multiplied by this cosine theta, right? And we will discuss a little bit more in the next few slides about this concept projection, because it will be important when you consider a free rotation chain model. And we would also consider the dihedral angle as shown here. And dihedral angle is how much you can rotate in the polymer chain. Okay? And this is a projection I has been discussing, that you would have different degree of projection. So let's say this bond as showing here in this green triangle will project along into this particular bond. Okay? So their degree of projection will be equals to Li plus L is the length cosine gamma. Okay? And this will be related. Let me make sure I use slideshow so that we don't change from current. Okay. And it will project once from this particular bonsai circling triangle into this region, okay, as shown here, project to here. If it's got one more projection, it will be equal to Li1 plus Li plus 1 plus L cosine beta, gamma, and cosine gamma again. So this would be equals to what we call it projection, the concept of projection of your polymer coil along its incidental angle. If you have question regarding this, make sure you ask the question during the live QA session. This is very important when we compute about free rotation chain model and how much degree of projection we have. We already discussed in the free joint chain, the outcome would be that our chain can adopt theta angle from 0 to 180 through whatever angle it like to take. Meanwhile, it would also allow the chain to adopt a dihedral angle from 0 to 360. If you satisfy those two conditions as shown here, this qualify your chains to be a free joint chain model, which in other words means this angle can be bond angle, can be any, and this dihedral angle can be any angle along its polymer rotation direction. So there is literally no limitation whatsoever. The end-to-end distance will be a consecutive will be the same as what we discussed. R square, end-to-end distance square, will be equals to NL square. Please be mindful that here the end-to-end distance has L square component in it. So if you only just want to know end-to-end distance, you need to take a root square of the previous term. So this tells you in the free joint chain, again, like we mentioned in the last lecture, it will be equals to number of bonds take a root square multiplied by length L. It will, if you compare again this to the contour length, as you can see, this value is much lower. This model is actually highly unrealistic physical model, as we show here. Why? Because it ignores several factors. There is no chain would be able to rotate that long, and there would not be any chains would ignore the dihedral potential. So in real case, the other two models we're going to discuss in this class, free rotation chain and hindered rotation chain, will be more realistic. However, people still use them because they are quite useful in many sense, that you can apply this into long polymer chain and it still get very reasonable results. So additionally, there's two conditions actually satisfy this free joint chain. We're not going to talk in a lot of detail, but please keep it in mind that there's two conditions. One is something called melt states. So in a polymer that is being surrounded by itself, the degree of repulsion and the repulsion from itself versus other chain, its neighbor chain, will cancel out each other. So effectively, you would have ended up a free joint chain. Okay? And additionally, there is another condition called Seda solvent condition. What this Seda solvent condition basically means that when your polymer chain is in a not so good solution, it's a little bit awkward, but it says it's not in such a good solvents, that it's not a bad solvent either. It's somewhere in between. You would be able to achieve that your polymer solvent interaction would be equal to cancel out the repulsive force from the polymer chain itself due to this excluded volume effect. But we will cover that in more detail in the later chapters. So for now, what you need to know is how does the free joint chain works, and how does end-to-end distance in the free joint chain relate to number of bonds and the bond length. Okay? So there is a concept that we need to be mindful is that degree of polymerization is not necessarily equals to number of bonds, as we already discussed in the polyethylene. In each repeating unit you have 2 carbon-carbon bond, or in this case I showed again, in polybutyl methyl methacrate, in each repeating unit you have 1 bond here and half bond on each side, and this half bond, the reason for we put in half there is just because they were shared by 2 neighboring polymer. Okay, so with that, we would be able to compute that number of steps in the random walk will be twice of number of degree of polymerization. Okay, so this would be the case if each repeating unit you have 2 carbon bond. If your repeating unit is longer, which I will show in the next slide, if you have polyethylene chain, in the backbone then you would have 1 carbon-carbon bond and 2 carbon-oxygen bond in this case. So this repeating unit will be different with what your case has shown. Again, but in the free joint chain, because the cross turn, as we talked about, if it's not self-turn, because of free joint chain models intrinsic ability to cancel out those turns, so your cross turn will be equal to 0. So what only left is the self-turn, and the self-turn you can also treat it as 2 separated bonds, and it's just to count the bond number as well as bond length. For example, in the PEO case, you can calculate out that the end-to-end distance will be equal to number of carbon-carbon bonds, bond length square plus number of carbon-oxygen bond, and bond length for the carbon-oxygen. Okay? So this shows how robust the random walk can be used to understand what's the end-to-end distance for various polymer. Next is, if we consider that a little bit more realistic case. So what do we mean by a little bit more realistic? Your polymer will have limitations in the bond angle, but not in the rotation dihedral angle. So the rotation angle is understandable, that if you have carbon-carbon bond, the bond angle is fixed at 109 degrees, as I mentioned for a couple of times. So this free rotation chain model differs with free joint chain that the rotation angle will be fixed. Okay, so this bond angle gamma will be fixed in free rotation chain model. Well, in the previous case, it is not fixed, so that's a major difference. How this would impact our understanding in end-to-end distance. I already mentioned that I want everybody to guess about if it's increase or decrease. So here is the time for us to uncover the finding. I will explain the concept first, then go a little bit detail about why this is happening, and explain also in the mathematic ways how you can derive this relationship. So if you are interested in deriving the relationship, we have another separate YouTube video. You're welcome to take a look. But in a short sense, I'm going to repeat the important finding 3 times. The fixing of the bond angle caused an increase in core size. It is kind of understandable that if you fix the bond angle to be more directional, that would result in the chain to going further along the backbone direction, right? And how much degree of expansion can be simply used the equation down below. And how do we get there? This can be calculated mathematically through 2 ways. You would have a self-turn and a cross-turn. This is universal. So this equation does not depend on any chain model, and you can just use this equation to calculate it out. The first part is where NL square is a self-turn. So it's the same as showing this here. Again, this would be the self-turn. Okay. And you would have cross-turn for free rotation chain. And if you are interested to know how this worked out, so this should be referred to my other YouTube video. I'll post a link so that you guys can look it up and understand a little bit better why this is happening. Adding these 2 together, those 2 terms, you would have basically come to the conclusion that end-to-end distance will be NL square multiplied by a 1 plus a cosine beta and a 1 minus cosine beta. And as you can see, this become what I put in the box is additional term happened due to the introduction of the bond angle. So let's plug in a few numbers to help everybody understand it. What if this bond angle shown here is fixed at maybe 60 degree? Okay, so you can see this cosine 60 degree would be equal. The cosine 60 degree would be equals to a half. So 1 plus a half cosine 60, 1 minus cosine 60, another half. So this will be equal to 3 multiplied by NL squared. So your chain core size end-to-end distance is increased by root 3 multiplied by NL squared. Remember, this has a square term here. So if you take out square term, the cosine theta would result in 3 times increase in the core size. Next, let's talk about this new finding. This now says that the bond angle now would start to increase your core size. But what is important is that although there is increase in the core size, one important factor that your end-to-end distance is still proportional to NL squared, right? Although there is going to be a constant in front of it, but R squared is still proportional to NL squared. What this means is that if you still think about how much degree of parameterization increase would impact your end-to-end distance, it still scales with n power of 1/2. So this finding is basically the same as free joint chain. In other words, free rotation chain causes some sort of expansion in the core size due to the fixing of an angle, but it didn't change fundamentally how free joint chain would work out. And we can actually show a couple calculation about how does this end-to-end distance would changes with different degree of expansion. So for example, if we have a bond angle, this gamma term, let me show bigger. Oh, so sorry, this should be theta angle is the bond angle. So it can be a little bit confusing, depends on which textbook you use. But if you use theta, and now this, remember, because the gamma term and theta term differs by a pi, so pi minus theta would equals to gamma, and this causes a little bit confusion for some of you. This would be written as 1 minus cosine theta. It's basically the same as 1 plus cosine gamma. Those equations are interchangeable because these two bonds are differs by 90 degree, pi minus that degree, okay? But now, if you think about the bond angle again, that's determined by how big the opening of your bonds are between neighboring one. If the opens very large, that means, for example, 109 degree is what we discussed, is similar to sp3 bonds. That results in 1 minus cosine theta divided by 1 plus cosine theta equals to 2. That means your chain is expanded by root 2, okay? And as you can see, the more straight the bond angle is, the more expansion you would have. That also makes sense because if it's perfect 180 degree, you basically have a rod. If it's 179 degree, you are closer to a rigid rod, so your chain will have a larger end-to-end distance. This has also been verified in different calculation and mass data, as you show. We plot r square, which is end-to-end distance, versus number of bonds. And depending on different bond angle, we can calculate out how they would depend on those bond angle we have discussed. Next. Free rotation chain is not only limited to carbon-carbon bond. You can also consider multiple bond angle would happening. So show here we have the PDMS on the top left corner, or polyphosphazine on the right, and those two molecular, you would have two bond angles along the polymer chain, right? So you got to have gamma 1 and gamma 2, those two kind of bonds. So how this would impact, you would have an average of gamma 1 and gamma 2 in the final findings in your bond. But again, it doesn't change the conclusion that your chain conformation will depend on m power of 0.5 end-to-end distance. This is still the case. And we will come to the conclusion that we can actually later, we can summarize this term to be a constant called a characteristic ratio, and we will go through that in just a moment. So now we have the time to talk about rotation isomer state. So what is rotation isomer state? Rotation isomer state is basically saying that now consider not only just the bond angle, but this phi angle has preferred state. What that mean? That means we would have that a bond that not only would take up a rotation, but it has a certain preference in terms of rotation. And we can see in the next slides, this is what we talked about in the gauche plane or trans, or gauche different rotation. And we would also has ellipse rotation, where you have the bond is sitting directly on the bottom of the large bond. This would result in a higher energy, and again, this is a good cartoon showing which direction we should look at. We are basically following along this carbon-carbon bond. And now you would have 3 units. You have unit 1 and 2 and 3. And those 3 units would translate to those 3 units, okay? And there is, again, we can mark this carbon would be 4, and those hydrogen would be 5, 6. So this would be translated to those 4, 5, 6. So now you rotate around these 2 planes, and they would causes some of the area you have bond is sitting on top of each other and causing stirring hindrance. In some cases, they wouldn't. And as you can see, this is nicely presented in this energy diagram. This plot as energy potential versus bond angle. What this says is when the bond angle is in the trans states, when it's rotated at 90 degrees with respect to each other, it has lowest energy. Well, it's a gauche, two of gauche states. It has also increased energy, but also a local minima. And you can understand that because your chain is sitting in not overlapping on the other state, but also a local energy minima, right? And this trans will result in minimal bulkiness because these two are large chain groups. And when they are getting close, they create a lot of energy stereo hindrance, like in show here, where you can see this would be representing this states. They would represent in both high energy states. And start rotating, then the chain would go to the gauche states. So these would be represented here. And you keep rotating until it's in the planar state, which is lowest energy. Good. So rotating isomer state is basically says you would have two gauche plus minus, and a trans state will be preferred by your material's property, because when you rotate into that energy, it will be lower energy. And we can use that to calculate the cosine theta, which is average of the rotation isomer states. So this would result into additional expansion of your polymer chain, because now it's not rotating in plane freely. It now has a three state is preferred: gauche, trans, and gauche minus. This results in this term. We call it further expansion due to the rotation isomer states. Okay, so is it clear that what this rotation isomer states is? It's basically is additional restriction compared to free rotation chain, resulting your chain to apparently expand. And how big they expand due to this rotation isomer states is also, again, depends on this cosine phi angle. We don't need to worry about those. So in this slides, we're going to talk about the concept now called characteristic ratio. As we talked about, when you consider there's two states, one is we call it a rotation isomer state, the other is called free rotation bond states. Those two restrictions we put into the system would always result in a slightly increase your core end-to-end distance. However, it doesn't change fundamentally how the coil behave. You still follows NL square states. So instead of using the 1 plus cosine theta divided by 1 minus cosine theta and multiply the similar term using the phi angle, we now can just say we want to conclude all these into one parameter. And this parameter is where we're going to discuss in this slide. It's called characteristic ratio. Showing here. So what is a characteristic ratio? In a simple layman's language, characteristic ratio is what is described as degree of expansion for your polymer chain. So if you have high expansion ratio, you would have a high characteristic ratio. Okay, so if you have characteristic ratio of 10, that means your chain is expanded by root 10 is almost 3.3 times compared to without any characteristic ratio or free joint chain. And you can see basically this is defined as NL square is basically the theoretical end-to-end distance. This is also the Gaussian chain end-to-end distance, and where you actually your chain distance. So what you will see is the free rotation chain independent rotation chain. This is basically also is called free rotation chain model. Okay, the same. And this is a hindered rotation chain model or rotation isomer state. They would result in different degree of expansion. As we show here, we have almost no expansion to some expansion up to 3, then a lot of expansion to 2. We consider bond angle and dihedral angle. Okay, so this is due to fixed phi and theta. This is only due to fixed theta. We don't consider the dihedral angle. So Cn is basically called characteristic ratio. It's also called a Flory ratio. Okay. And a few polymer we have known has been characterized and plotted here. So for example, we know that polyethylene has a characteristic ratio of 6.7. Polystyrene has a characteristic ratio almost 10. PP has a characteristic ratio of 5.8, and etc. And the polycarbonate has 2.4. So polycarbonate is most closer to free joint chain model. But the others all shows some degree of expansion. The chain is slightly bigger than what it is supposed to be, right? Okay, but if you consider a more realistic model, then you would have where you have bond interference. What that means is your long distance bond will interfere with each other. This can sometimes be conceptualized into different energy potential states, as shown here. So not necessarily you would have trans-Gauss, because your chemical monomer structure will get more complex. You will generate a very complex chemical potential map, as shown here. All right. So this tells you that although a hindered rotation chain model is close to reality, but it's still not. And we're gonna discuss a few more minutes about what's the real chain look like versus those chains. In the real chain, we haven't touched base is something called self-avoiding walk. Random walk basically says your next step will be random. Self-avoiding walk is a similar concept, except that you says you cannot walk on the previous step, so you have to avoid yourself. So self-avoiding work is more realistic. And due to self-avoiding work, we will see that our chain is also expand. And degree of expansion is shown in the polymer in the good solvent, not depends on m power of 0.5 L, but instead it will be m power close to 0.6 L. And this power of 0.6 is an expansion factor. And we will discuss more when we talk about polymer in different quantity of solvents. But this should conclude today's lecture, where we discuss there is two additional model, free rotation model and hindered rotation model, or also called rotation isomer model. And in those two models, although we are getting closer to where a real chain is, but it's still not as ideal. But it's a good approach for us to understand how these chains would expand. And degree of expansion is also called a characteristic ratio. And if you know the characteristic ratio, you can apply that and use a simple equation Cn infinity multiplied by NL squared to calculate out what's your end-to-end distance. Again, you can count how many bonds and count the bond angle and just apply the C infinity parameter. And C infinity parameter can be also related to bond angle and rotation angle. So rotation angle and dihedral angle. So these two will be reflected in the calculation where you have 1 plus cosine theta and 1 minus cosine theta. So I hope this will be helpful for you to understand what the difference between those three models. And I'm happy to answer the question in the live session. I'll see everyone later.